humans. We're going to do 3.2 today. We're going to be talking about logarithmic functions. We're going to recognize and evaluate log functions, and then we're going to graph and solve log equations. So let's go back and talk about our exponential functions first. And those were y is equal to a to the x. And then let's talk about just this one for right now. So if you'll remember, this function is 1-to-1, which means it passes the vertical line test and the horizontal line test, which means that its inverse, a, is possible, and b, the inverse, is a function. Well, it just so happens that the log function is the inverse of the exponential function. So that's kind of cool. And the log function is y is equal to the log base a of x. Alrighty. And then if you solved this equation you would get x is equal to a to the y. Alrighty, if we solved for x, this is what we would get. So it's just how we would flip-flop the variables, and then we would solve for y when we were calculating inverses. So that's actually kind of cool that the two functions are inverses of each other. So the first thing that we're going to do, I'm not actually going to solve this for y, but we would get there eventually, is I want to talk about changing forms. But it is cool to note that the log and the exponential functions are inverses of each other. And remember, that also means if I do a composition, I would get x. When we study logs, we will spend a significant amount of time bouncing between these two forms. So if something is given as a log, maybe I need to go back to exponent form, and vice versa. Maybe they give me something in exponent form, and I need to take the log of both sides to make sure that I can manage the equation. So let's talk about log form. So let's say something is given as the log base 2 of 8 is equal to x. Well, if I want to go to exponent form, that would say 2 to the x is equal to 8. And then I could solve that using the 1-to-1 property because this is 2 to the third. So remember that we learned the 1-to-1 property different than a function being 1-to-1, but the 1-to-1 property would allow me to solve this because this is then 2 to the third, and then I would get x is equal to 3, the baby equation at the top. But we will spend a significant amount of time bouncing between these two particular forms of the equation. So let's do an example. The first example says, I want you to solve, and I have the log base 2 of 32 is equal to x. Well, because the problem is starting in log form, I'm going to shift to exponent form. So I'm going to write this out here just to make sure that we understand. This is log form. So I'm going to go to exponent form, because it started in log form, so I can go to exponent form to solve. 2 to the x is equal to 32, which is 2 to the fifth. Now my baby equation at the top, x is equal to 5. So that was actually really pretty easy. The second example, example number 2, same direction, solve, and I have the log base 10 of 1 over 100 is equal to x. This is log form. To be able to solve, I'm going to go back to exponent form. Okay, so I'm going to get 10 to the x is equal to 1 over 100. Okay, move it up so you can see it better, my bad. 1 over 100 is 100 to the negative 1. 100 is 10 squared raised to the negative 1, so this is 10 to the negative 2. Well, now the 1-to-1 property kicks in because the bases are the same, and I get x is a negative 2. So that's actually pretty simple. And logarithms, if you remember the basic rules, are really fairly straightforward because they just bounce back and forth between the two forms. A common log is one where I have a base of 10, and so we would write that as a log. So we typically don't write the base, so we would just write this as a log. The natural log is a base of e, and so instead of writing a log base e, we write this as a natural log. Both will give you a value for an equation, and it doesn't matter often which you use, but you need to be careful when you're switching forms which base is given. So now let's talk about the graph of logs, because it's kind of cool. All graphs are kind of cool, actually. So here's my handy dandy coordinate system, and then this is a 1. The graph of a logarithm, we'll do it in a different color so you can see, looks like this. There's not a vertical asymptote at x is equal to 0. All of this is undefined. So this is undefined, which means that you cannot take the log of a negative number. So if you have the log of a negative 3, that doesn't exist because you can't take the log of a negative number, right? The standard logarithmic function crosses at 1, at x is equal to 1. If I translate the graph, then this particular asymptote moves with the translations, okay? All right, so let's talk about this. Technically, there's a vertical asymptote at x is equal to 0. The domain is 0 to positive infinity. The range is all real numbers. The x-intercept is going to be 1, 0. This particular function increases over its domain, and this particular function is 1 to 1, which means that it passes both the vertical line test and the horizontal line test, okay? All right, now let's talk about the properties of logs, which is short for logarithms. I'm just a little bit too lazy to write out the whole word. If I have the log base a of 1, that equals to 0, and if you put it in exponent form, a to the 0 is equal to 1, anything raised to the 0 power is 1, so that's kind of cool. The next one is the log base a of a is equal to 1. And again, if you go back to the other form, it makes sense. A to the first is equal to a. Yep, we know that's true. The next one is the log base a of a to the x is equal to x. So if you think about the same thing, go back to exponent form. A to the x is equal to a to the x. Yep, that's also true. And the log base a of x is equal to the log base a of y. Then because the one-to-one property, so notice that this is the same and this is the same, if the logs are the same on both sides of the equation, the logs disappear, and this says x is equal to y. This is absolutely one of the most powerful things with logarithms. It's hugely helpful in calculus. So I'm going to start with some examples. This one is example 3. The directions say simplify. And I have the log base 4 of 1. And because the equation is given like that, I'm going to really turn it into an equation, and I'm going to put an x in there. So now I'm going to go back to exponent form. So 4 to the x is equal to 1. I get a 1 if x is equal to 0. And that was actually kind of polite. All right, let's do example 4. Example 4 also says to simplify. This time I have the log base radical 7 of radical 7, and then I'm going to put in an x. okay? And then I have radical 7 raised to the x is equal to radical 7. Technically, it's 1. Therefore, x is equal to 1. All right, next example. We'll do example 5. These are all just nice, simple little problems. Nice, polite start to our logarithms. If I had the log base 3 of x is equal to the log base 3 of 12, love these problems. This is the same as this. Therefore, by the one-to-one property, those go away. X is equal to 12. Doesn't get much better than that. Okay, now let's do example 6. Same directions, simplify. And if you haven't noticed, basically all we're doing is walking through the properties of our logarithms. So if I have the log of 2x plus 1 is equal to the log of 3x, notice that the 10 is not written. And if the 10 is not written, it's assumed because that's what a standard log is. This is, again, the same thing. It's the one-to-one property. The logs are the same on both sides, therefore they go away. And I get 2x plus 1 is equal to 3x. And then 1 is equal to 3x minus 2x is equal to x, and therefore x is equal to 1. That was nice and easy. All right, so now let's talk about transformations, because every equation group that we study means that it can be transformed. And again, just like when we talked about exponential functions, we have the same rules. So I'm not going to go all the way back through that, but we're just going to do a quick little example. So let's say my original function is the natural log of x. And remember, that would look like this. It would cross at 1. Well, the new one that has been changed might be the natural log of x minus 1, which means that the function and the asymptote are going to shift 1 unit to the right. I'll do that in a different color. So my vertical asymptote here is x is equal to 0. So now that means it's going to be here at 1. And if the x-intercept was at 1, now it's going to be at 2. So now the function looks like that. Okay? So the exact same rules apply. All right, I have just a few more examples for us, and then we'll be done for today. So example 7 says, again, to simplify. And I have the natural log of 1 over e is equal to x. Remember, in a natural log, it is a log base e. So the base is e. So I'm going to go back to exponent form. E to the x is equal to 1 over e, which is just e to the negative 1. Now the one-to-one property applies because the bases are the same, so I get x is equal to a negative 1. Okay, example 8. We're just cruising right along. Again, such complicated directions. Simplify. E to the natural log of 5 is what I want to simplify. It's easier if I make it an equation. Go back to exponent form. Actually, I lied. This is already in exponent form, but it looks a little bit weird, so I'm actually going to convert it to log form. So I'm going to say the natural log base e of x is equal to the natural log of 5. And so what I did is I went from exponent form. So this one is in exponent form. And I went to log form. I just happened to I chose the base of e. Boy, somebody likes me today. And because I chose the base of e, now the one-to-one property kicks in, which is lovely. So now I have x is equal to 5. All right, just a couple of more examples. Is that true? Let me take a quick peek. Yep, just 2 more. So the last one that we have to do says describe the transformations to y is equal to the natural log of x and state the domain. Okay, so we're going to do a couple. The first function says f of x is equal to the natural log of x minus 2. The 2 is inside the function, so that means this is going to go right to, remember it's the opposite sign, so that means that if my original function looks like this, and I go right to, that means now that the vertical asymptote is at 2, and then if I originally crossed at 1 and I add 2, this is now going to be at 3. So the domain is going to be from 2 to positive infinity. Being able to graph the original and what happens oftentimes makes it easier to develop what your domain is, especially if you're doing it by hand and not in your grapher. The next one, g of x is equal to the natural log of 2 minus x, looks very similar, so I'm going to rearrange this though. This is the natural log of a negative x plus 2. Remember, we always factor before we start, so this is the natural log of a negative times x minus 2. So this is a reflection across the y-axis because this is inside the function, and then I am going to go left 2. Alrighty. My domain then, and this is our last example, so let's think about the original. The original, here's your vertical asymptote, and it crosses at 1. So the first thing that I'm going to do is I'm going to reflect it, which means it's going to cross at a negative 1. And then I'm going to move everything 2 to the right, so that means that this is 1, 2. Now I cross at 1. I'll do it in a different color. So this is going to be the function, and then that means at 2, that's going to be your asymptote. Good gravy. So the domain is a negative infinity to 2, not included. Alrighty, that is it for today. I will see you soon.